Okay, so this lesson, the next page for it is a worksheet. I included graph paper because the textbook questions that are listed as homework, you need graph paper for it. We are going to do a graph in the virtual lab, so if you want to just do that, that's okay. However, remember, when you come back, Monday, Block C, there's going to be an open book quiz. So the more stuff you have in your notebook, the better off you will be. You can't use your textbook, okay? So use your class time today wisely, and then you really will have no homework for this class in case your next week is a little bit heavier. The first little bit of this lesson is going to be going through some definitions, and then we will get into the math. So one of the whole points of this unit is describing the concentration of a solution, or how much solute is dissolved in solvent quantitatively. So we're going to do grams in milliliters or grams of water this morning, and then in the afternoon we're going to do different calculations. So if you have a water bottle that's not refillable, it'll list the amount of ions as parts per million, or ppm, ppb. If you're a news reader and you listen to how they describe the amount of carbon dioxide in the atmosphere, usually it's listed as parts per million. We'll look at calculating molarity, or moles per liter. So changing the amount into moles, which will then lead us to stoic. Okay? So like I said in the last unit, really kind of the end of a section is always going to be applying things using stoichiometry. But today this lesson, we're just going to stick with grams and milliliters. So solubility, the definition is the quantity. So again, the amount of solute dissolved in a specific solvent. And you have to have a very specific temperature as well. We just talked about the idea that changing the temperature can change how much of something dissolves. So a solubility curve is a representation of different solids and how it changes the amount that can dissolve. I can't photocopy in color. This is on page 394 in your textbook. I tried to include it in the note a little bit bigger at the bottom here, so that you could see it a little bit better. But even like the light sodium chloride line can be hard to read. So this is in your textbook. Or on the test or exam, it'll be something more like what's on the worksheet, where it's really, really dark. The lines aren't colored, but it's much easier to see the grid lines, okay? So this is on the worksheet, something more like that. You can ask a variety of questions based on a solubility curve, so that's really what the examples are. We're going to use the same solubility curve every time and basically just do different examples, okay? So usually the water amount is 100. It can be 1,000. So you just need to carefully read the units on the side of the graph. Temperature will always be on the X. And what the solubility curve is representing is the maximum amount in mass of solute that can be dissolved. So the curve sort of represents the saturation point, which is the greatest amount of a substance that can be dissolved. But again, it's temperature specific. Okay, so when you're asked a question, you're often given the solid, because it's different for every solid, an amount, and then a temperature. So one of those three things will be missing. Okay? And then we call it a curve because a curve, you can call something a curve that is a graph Usually you think of linear graphs, and some of them are lines, but some of them are not. They increase much more rapidly as temperature increases. But again, temperature will always be on the x and solubility is always on the y. So when you do the investigation, I've sort of made the scale for you, but you want to put temperature on the x and solubility on the y. So there are three kinds of solutions that can be described using a solubility curve. So an unsaturated solution means that more can be dissolved, so you're not at the maximum yet. A saturated solution is the maximum. So that's why on a curve, the line represents the saturation point. So again, it's the maximum quantity, but it has to be at a specific temperature. And then you can make a solution that we call unstable, which is a supersaturated solution. And it contains more than the maximum quantity of a solute than it should. So what you've done is put some solid in, it doesn't dissolve, and then you increase the temperature to make the solid dissolve more. That creates a situation that is a little bit unstable. So you can add even one more crystal to a solution to get it to dissolve. There's even some supersaturated solutions where even like bumping it or agitation will make it recrystallize. Again, if you're a YouTube watcher, this one, so you can see that the solution is clear, and then they're going to add one crystal, and you can see that it's coming out of solution. It kind of looks like snowflakes, right? Those are crystals. So sodium acetate is cheap, so it's a very common solution. So you can see how quickly it changed based on, it's called a seed crystal. So one little thing was added and it totally made the recrystallization occur. So supersaturated solutions, well, yes, it's possible to get something to dissolve more than you normally would. They are very unstable. So generally speaking, in chemistry, we're trying to find and represent where is saturation, okay? So if you have a solubility curve, saturated is the point right on the line. If you are at a value that's below it, then it's unsaturated. If you're a value that's above the line, then the solution is considered to be supersaturated. So we'll do that kind of example. This picture, again, is from your textbook. It's trying to show you basically what that video just showed. Nothing, add a seed crystal, and recrystallization starts to occur. So mathematically, we can figure out how much would come out of solution or recrystallize using the solubility curve. So that's one of the type of examples we can do. It often looks like snowflakes as it recrystallizes. So you can cool it, you can agitate it sometimes, depending on the solution, depending on its stability, to get recrystallization. So this is, again, I blew it up to try to make it a little bit easier to read on your sheet. Temperature on the X. We are in Canada, so we're going to use degrees Celsius. When you make your solubility curve, you must have units. You must. Solubility goes on the Y, or the amount. Usually, and for you guys, we're going to use grams of solid per 100 grams of water. Why can we say grams and not milliliters? Grams and milliliters are the same. They are considered to be equivalent units based on the density of water, which is 1. That is not true of everything. But when we build a solubility curve, we are going to use water. So sometimes it'll say grams per 100 grams of water, or sometimes it'll say grams per 100 milliliters of water. That means the same thing, okay? You should have a title as well for your curve. Solubility curves of ionic compounds in water, solubility curves for different ionic compounds in water. If you're doing one specifically, then you would say solubility curve for whatever. KNO3 in water or whatever. Make sure you have a title for your graph. And then make sure you have the appropriate units. So always temperature in degrees Celsius, usually, and for us when you guys do the investigation, solubility in grams per 100 grams of water or grams in 100 milliliters of water. Either one. And again, this is page 394. If you still don't like the way it printed, you can look at that. And if you want to reiterate for yourself, okay, so saturation is different for each solid. None of the lines are perfectly crossed the whole way down and for different temperatures. Okay, so let's do some examples. So we're going to look at the given information and decide whether the solution is unsaturated, saturated, or supersaturated. So we are given grams, we're given a solid, and a temperature. And what we're going to do is we're going to look and see and decide, is it above the line or supersaturated? Is it right on the line or saturated? Is it below the line or unsaturated? So unfortunately, if you take a look at your textbook, people might have actually written in the textbook because that is a good way to try to do this. So you go to 40 grams, which is here. Again, if that picture on here is too small, take a look at the bigger one maybe, okay? Then you have to, so 40 grams and KCl, which is this line here, and 70 degrees. So I'm going to go across. And find where they meet, 70 degrees Celsius, 40 grams. That's this point here. And then I look at KCl. Is the KCl, is it on the line? No, so it's not saturated. Is it above the line? No, it's below, so it's unsaturated. You don't need to, this kind of question, you don't need to explain what you've done, but I'll write a little explanation here. So again, the next one, 80 grams, which is way up here, and 20. Is this point here? Now I check what solid am I talking about? KNO3, which is this line here, this orange line. So is it on KNO3's line? No. Is it below? No. This time it's above, which is super saturated. The last one is 45. So when you do a test or quiz, usually I try to pick nicer ones, like 45's in between, or I would accept a variety of answers. If it was something where you had to say, you know, how much, like you had to give the grams. This might be helpful, maybe if you have a ruler or even the side of your calculator to use as a ruler. Might be a little bit easier. So we're going to do 45 and 40. Even that I don't think was perfect, but I did my best. So 40 degrees Celsius is right on a solids line. Which solid is it? Oh, it's NH4Cl. Is that my solid? Sure is. So when it's on the line, saturated. Okay, so that's one kind of example. Turn the page and we'll do some more. This one is knowing the definition and looking at the curve. The next kind of example is you don't have to know whether it's unsaturated, saturated, or supersaturated. We're going to look at now, we're going to use the curve to find amounts. So this question is asking us how much solute will dissolve at each of the temperatures. So we're going to do a warmer temperature and then a cooler temperature. And then we're going to look at how much will recrystallize. Okay? So again, solids, you have to be specific. So we're going to do NH4Cl first, which is this blue line. Okay, NH4Cl. 80 degrees Celsius, so 80 degrees. So again, maybe even if you don't have a ruler, it might be helpful to use like the side of your calculator. So 80 degrees, go up to NH4Cl, and this is where you might need to estimate. So I would accept a variety of answers, but make a good estimate, okay? So here, you go over I might call that 65 or 66. I'm going to say 65 grams. So at 80 degrees Celsius, 65 grams of NH4Cl dissolve. Now, temperature number 2 is 20, so we're going to cool it down. So if you know the trend that when you increase the solid or increase the temperature, more solid should dissolve. So then likewise, if you decrease the temperature, you should get less. So you should get less than 65, and that's a big jump. So quite a lot less probably. So now we're at 20. Okay, so what's that going to be? And you can see my line's not straight. That's terrible. Let's try that again. I would say above 35, like 37, maybe 38 you wrote down. Definitely above 35. So again, a variety of answers I would accept. Okay, so then this question says how much will recrystallize, the chart. So it's up to you if you want to do all of the solids first and then go figure out how much would recrystallize. It really doesn't matter. So if you are at temperature 1 and 65 grams dissolves, and now you're at temperature 2, which is 20, and 38 grams will dissolve. So it says how much will recrystallize. You could dissolve 65. Now you can only dissolve 38. How do you figure out how much recrystallizes? All you have to do is subtract. And to get full marks on a question like this in a chart form like this, you could just show your final answer and get full marks, but I'll show. So 27 grams can no longer dissolve. We could dissolve 65. Now we can only dissolve 38. That means 27, or the difference between them, is how much is no longer going to dissolve. So I'm going to pick a different color and go to KClO3. This time it was 60 and 25. I'm going to say 25. It's pretty close to 25 grams. So this one maybe more like 9. Now you can only dissolve 9 grams at 25. So you could have put, I think 25 is pretty close. Maybe this one you put 8. That's okay. Has to, I would say, definitely above half, right? Now we're going to do K2SO4, which is the red line. 30 degrees. I don't know, what would you call that? Like 12 grams? Maybe 11? I would accept that too. This one's kind of ugly. So to me, it still doesn't seem. It's not quite 10. You might even want to write 9.5. So you can see that when you have to do questions like this, you're visually determining it, right? So then anytime you do something like that, I would have to accept a variety of answers. Now, within reason, so this is a type of question you can do using the curve, figure out how much dissolves at one temperature. If it goes from higher to lower, then it would be how much it recrystallizes. You could also be asked the reverse. Start with the low one and then go to the high one. How much more can dissolve, but you would still be subtracting. Okay, and then for these two questions, it's a little bit more general. So how much KNO3 dissolves at 80 degrees Celsius? So if you look at 80 degrees for KNO3, and you do the same sort of thing, the curve never crosses 80 degrees, right? So it's way, way, way theoretically above. So you would just have to think of the trend. The KNO3 line is continuously increasing. So how much is it? We don't know, but likely it's logically, according to the trend, it's probably above or greater than 100. You could also be asked sort of general questions like this. At 40 degrees, what substance is the most soluble, like would have the most dissolving? So you go to 40 degrees. Oh, did you see that? I like that. If it was a question like this, it would have to be really obvious, okay? So the most soluble, most or greatest amount. Which one has the greatest amount dissolved at 40 degrees Celsius? It's obviously KNO3. So I wouldn't pick something like in here where the lines are really close together. I don't want to, in a question like this, I wouldn't want it to be open to interpretation. Very clearly, what's the answer? So the solid that is the most soluble has the greatest amount of dissolved, which is KNO3. But again, you do have to be given something. So you have to be given a temperature because the temperature obviously changes how much dissolves. And then the last kind of example has to do with, deal with ratios. So sometimes people will actually call this solubility curve stoic. It's not really stoic, but we are going to write a ratio. So it sort of resembles stoichiometry. So I get it, but it really isn't technically stoic because we're not using coefficients. Because there is no reaction yet, okay? All we're simply doing is dissolving a solid in water. Okay, so Billy wants to dissolve 5.5 grams of sodium or ammonium chloride in 10 milliliters of water. So here's the problem. So it's 10 milliliters of water, but our curve is 100. It is not the same. So in order to use the curve to find the temperature, we have to change it into 100, which we can do. And we want a saturated solution, so that means we want it to be right on the line. Okay, so by definition, a saturated solution would be the amount dissolved on the line, the saturation point, for whatever solid. So our question says NH4Cl. In order to use the curve to find temperature, which is what the question asks for, what temperature should his water be at, then we have to, in order to use the curve, it has to be 100, and it's not. The question says 10. So you can write a ratio. Again, that's why I said sometimes students look at this like stoichiometry. Now, this one, if you're, mathematically inclined, is 110. Those are easily factorable, or you can sometimes, if you're mathematically inclined, see how much it is bigger than, how much 100 is bigger than 10. But if not, if they're not nice like that, 110, you can do the same procedure every single time, okay? You guys have lots of space, so you don't need to squish on your note. I kind of have to squish down here. I apologize, okay? So there also are questions, a variety, they could be variety, where you do have to write a ratio. It could give you the temperature and say how much dissolves and then ask you to change it into a different amount of water. You can do that too. In this case, it's saying 5.5 grams in 10 milliliters, but in order to use the curve to find the temperature, we need to know how many grams are able to dissolve in 100 grams of water. Given 5.5 grams in 10 grams of water. Where did I get the 5.5 and 10? I got it from the question. Right now, when we do this math to convert it into out of 100, technically we don't even care that it's NH4Cl. The only time that we're going to care that it's NH4Cl is when we have to go figure out the temperature. Okay? So if you want to simplify your ratio and you want to leave it out of here, you can. If you want to write it in here, you also can. They do need to match NH4Cl, NH4Cl. Water, water. Okay? So it's not useless to write it in there, but if you like things to be simpler, then you can leave it out of your ratio for now. So now this looks more like what we've been doing before, where you can do inverse operations. So 5.5 divided by 10 and then times 100. Or if you're a cross multiplier, you can do that same math here. Doesn't really matter. Again, maybe you see that 10 is one, or if you're going this way, 100 is one more decimal place than 10. So if we're talking about 5.5, our answer is going to be 55 in 100. You can do that as well, but you can always, always, always do this ratio if they don't match nicely like that. You know what? I'll cross multiply, but it really doesn't matter. You can do inverse operations. X times 10, 100 times 5.5. Decide how much work you want to show. .5 times 100 is 550. Again, you can see that this is 2 zeros, so that's going to be 2 decimal places. Maybe you mathematically think of it like that, which is totally fine. You get 550, but we have to divide by 10 to isolate x. Sorry that I'm squishing. You guys don't have to squish. So you get 55 grams of NH4Cl. Don't do the hard work and then forget to find the temperature, because really that's the straightforward part. So we have 55 Sometimes it'll be nice, sometimes it won't be. This one does happen to be nice. So go over to NH4Cl and then down. And it happens to be right on 60. So when you do these questions, it is helpful to keep units. So I wrote X grams so that you know when you solve for X that you're getting grams, not degrees Celsius, which then means you need to go and use the graph or the curve to find temperature. Okay? So this question, obviously beefier than the other questions, this question would be out of more marks. So then maybe that's hopefully your clue. You have to do a little bit more work.